So today let's see binomial theorem for any index. Binomial theorem for any index n. Now, what is the meaning of any index? Let me clear you. Earlier, we have expanded a plus x to the power n, where n was natural number. If you can remember, at that time n was a natural number. And the expansion was like nc0 a to the power n, nc1 a to the power n minus 1 x to the power 1, nc2 a to the power n minus 2 x squared, ncr a to the power n minus r x to the power r, and at last ncn x to the power n. So this theorem was for any index n, for natural number, sorry. Now, what we are supposed at present to expand is 1 plus x to the power n, where n is not a natural number. It can be a natural number, but you need to assume that n is like a negative integer, fraction, like minus 1, negative integer like minus 1, minus 2, fraction means 1 by 3, 1 by 2 kind of pure proper fraction. So these kind of things we can also use in this expansion, 1 plus x ka power n. You can take n as negative as well as fraction, whatever you want, fraction, negative, positive. So this n is applicable for all kind of values. That's why it is called any index. What is the meaning of index? The meaning of index is power, and this power is bound to be free from any kind of condition. So you can take it as an integer, negative, positive, you can take it as a fraction. But there is a condition like this x we are taking less than 1. In fact, mod x is less than 1. Like x is minus 1 to 1. Just like the GP series. If you can remember the infinite GP series. Now, what is the formula? The formula would be in the form of 1 plus nx plus n into n minus 1 by factorial to x squared. The fourth term will be n minus 1 n minus 2 by factorial 3x cube, like this. It will go up to infinite terms. So this is the reason we have kept this variable x in between minus 1 to 1, because this is an infinite series, and if you take x more than 1, then ultimately it will go up to infinity. The value will go up to infinity, and that is absurd. So you need to remember that this x is in between minus 1 to 1, and the number of terms for any index is infinite. Now, how to prove this? You can easily prove this, but for that, you need to have little knowledge of differentiation. At least you should know d by dx of x to the power n is equal to nx n minus 1. This much you should know. Okay, so let's start the proof. Let suppose 1 plus x to the power n is equal to a0 plus a1x plus a2x square plus a3x cube, and so on up to infinite terms. So what we have done, we have just taken the coefficients like a0, a1, a2, a3, and we have taken all the powers of the variable. Infinite terms. Infinite terms. Okay. So what is our requirement? Our requirement is to find the values for a0, a1, a2, a3. And I told you that we will be using the fundamental theorem of differentiation. D by dx of x to the power n is what? Nx n minus 1. Power is n minus 1. So this is the most basic formula for differentiation. Everybody knows it, I think. Now, how to find a0? See, this is an identity in x if my domain is minus 1 to 1. A kind of identity you can take where you can put this x in between minus 1 to 1, any value. So if I will ask you, you want to find a naught. So what is the most suitable value for x which you can use here in this particular identity, or you can say in this particular equation? Rather, we should say it equation because identity is valid for all x, and here x is only from -1 to 1. So I will call it an equation. So for this equation, the most suitable value for x in between -1 to 1 to find a naught is x equal to 0. The moment we put x equal to 0, all the terms after a naught is 0. And we will get 1 plus 0 to the power n is equal to a naught. Then to implies a naught is equal to 1. Okay. So we got the value for a naught. Now the next one is a1. Now here we will use the differentiation part. Suppose we differentiate 1 plus x to the power n, then it will come like 1 plus x power n minus 1 and multiplied with n. Now the differentiation of a naught is 0. Differentiation of a1x is a1. Differentiation of a2x square is 2a2x. Differentiation of a3x cube is 3a3x square, and so on. Now again put 0. The moment you will put x equal to 0, you will get n into 1 to the power n minus 1 is equal to a1. That implies a1 equal to n. We got the value for a0 and a1. Now the next one is for a2. So again differentiate this particular equation, equation 2. Suppose this is equation 1, this is equation 2. So differentiating both sides of equation 2. Then you will get n into n minus 1, 1 plus x power n minus 2 is equal to 0 plus 0 plus 2a2 plus 6a3x and so on. Again put x equal to 0, both sides. When you put both sides, you will be getting n into n minus 1 into 1 plus 0 power n minus 2 is equal to 2a2. That implies a2 is equal to n into n minus 1 divided by 2. So in this way, you can easily compare, like we are getting the three required coefficients of this particular expansion. So we can write 1 plus x to the power n is equal to, in place of a0, we can put 1. In place of a1, we can put n. In place of a2 we can put n into n minus 1 by factorial 2. And so on, up to infinite terms. So this is the proof of any index. Any index n. So there are so many students who keeps asking, like, if this n can be used like a positive integer. Definitely, it can be used like a positive integer, but that condition x lies in between -1 to 1 will remain, you know, will remain useful here also, because without -1 to 1 condition, you cannot have infinite number of terms, right? So for any index, n is applicable for all kind of positive integers, negative integers, fractions, but mostly it will be used for fractions and negative integers. Because for positive integer or natural number, you have this expansion. Now, another question which arise in the mind of students is like, when we use natural number n, a plus x power n, where n is natural number, then we restrict this up to n plus 1th term. So why not it is going up to infinite terms? See, the up to infinite terms is valid only for -1 to 1, because we don't want to diverge the series. This is just like infinite geometric progression series, where we put the condition -1 to 1 for common ratio. Because the moment you increase r up more than 1, then the series will diverge, and ultimately the last term, or you can say after a considerable number of terms, the value of each term will be infinity. So these two parts are, you should know, like these are not comparable, because here your x is free to take any values. In case of the index having natural number, this your x and a, they can take any values. But for any index n, we need to understand that our x is -1 to 1, and this n can take any kind of value. Okay, so I hope this is useful to you, binomial theorem for any index n, because it confuses a lot. And whenever we will use it, we need to keep in our mind, like the condition is on x also, which need to be varied from -1 to 1, and the number of terms will not be restricted. It will go up to infinite terms. Thank you.